In this episode of Woodlands on the Web, we'll be looking at collision theory and reaction profiles for both elementary and multi-step reactions. So to begin, let's start out by just talking about what the collision model actually states. So it basically says that you have to have enough energy and the right orientation of particles so that when they collide, they are able to make something new. If either of those criteria are not met, then you won't have a new product. This slide is a good example of how the orientation factor comes into play in collision theory. So this is showing you two reactants, a green particle and then this molecule here. And in this case, when they collide, the two green particles stick together and these two particles come apart as something different. So in this case, the way that the particles collided together as the activated complex, that's what this center kind of representation is. So this is your particles, both of your reactants when they're collided together. If they collide in such a way that they aren't able to stick in a new way and make something new, then that's an ineffective or unproductive collision, unfruitful collision. So again, basically just comes down to the fact that the way that particles bump into each other is going to determine or be one of the factors that determines if a new product is able to be formed. Let's first review a standard elementary reaction profile before we look at multi-step reactions. So this type of profile is showing you a set of reactants that are progressing to a new set of products. And this is where you have your activated complex. So this is where your particles are combined together. So if we were using pictures, you would be looking at something like these two separate particles added together. The activated complex is where they're all smushed together and collided. And then your products would be where you have them separated into a new type of product, a new substance. All right, so let's look at the different energies that are associated with this type of curve. So this is chemical potential energy that's listed over here. We'll hopefully be able to relate this a little bit more to bond angle energy and bond energy in general. So understanding that the inherent bonds within particles are going to have a certain amount of potential energy within them. All right, so since we're looking at the reaction progress going from left to right, then this energy, number 1, is representing the potential energy of your reactants. Okay, so the first plateau is always going to be your reactants. Plateau 2 is from the bottom of the graph from 0 up to the top of the hill. So that's specifically the PE or the potential energy of the activated complex. This is also known as the transition state sometimes. Number 3, however, is going from the reactants plateau to the top of the hill. So this is representing how much energy is needed in order to get the reactants to bump into each other and collide together. So that is specifically the activation energy. So that's the amount of energy that's needed in order to get the reaction started. So you have to have a certain amount of energy to allow the particles to bump into each other in the first place. And this is often abbreviated E sub A. Okay. Number 4 is referring to, if you'll look at the way the graph is drawn, this is the difference from the products to the reactants. So technically, you want to remember this as the products minus the reactants. So this is going to be your product energy minus your reactant energy, which is your enthalpy of the reaction. Okay, so this is often shown as delta H. Sometimes it's delta H sub reaction. And I also want to add here a number 5. And number 5 is going to be representing the potential energy of the products themselves. So whatever substance that is. In this particular curve, because our number for enthalpy is the products minus the reactants, we have a lower number minus a higher number. So in this particular example, our delta H would be negative. Okay, so that means that this particular curve is showing an exothermic reaction, If the plateau ended higher for the products than the reactants, then that would give us a positive delta H, and that would be representing an endothermic reaction. Feel free to pause this video here and sketch this for yourself if you'd like. This should be really similar to the one that you learned in honors chemistry, but if you want to refresh your memory, go ahead and pause right now. So if we're given a reaction mechanism or a proposal of one, we need to figure out if that reaction mechanism makes sense with what we were able to observe. So the couple important points here as far as what we need to remember in order to do that is that we need to see first that the elementary reaction equations involved add up to the overall reaction. So again, this is for when we have more than one step. We also need to have rate laws that are consistent with each elementary step. So we basically have to kind of add up our rate laws as well. So we're going to practice that here next. Take a moment to jot down these different elementary steps because these are going to be used and manipulated in order for us to come up with an overall equation for this reaction as well as what's actually going on with its kinetics. So pause here for a second so that you can jot down these equations. You also want to include the words fast and slow as they're labeled. Our first question is just what is the overall reaction here if these three small reactions make up a larger observation? So again, what we're basically saying here is that we're starting out with 2NO, and then at the end, we end up observing some hydrogen and some nitrogen, So when we're trying to add up these elementary steps to create an overall reaction that explains our observations, we want to treat this somewhat similarly to the way we treated net ionic equations. So we're going to look for things that are on both sides of the reaction arrow. This should also remind you of when we were balancing redox reactions in acidic medium. In both of those cases, when things are on both sides of the reaction arrow, we're going to cross them out because they essentially cancel each other out. So for example, in this case, we have N2O2 on the product and on the reactant side, and then that is going to form some N2O that gets used up as a reactant in the third reaction. So what we're going to try to do then is put all of these together. So since these are on opposite sides and they're also the same amount, they're going to cancel out. And that's going to leave us with these substances as our reactants and these substances as our products. And we are going to have to add those together because we're basically adding all three of these equations together to get something overall. So when we add all of that together, we get 2NO plus 2H2 yields nitrogen and 2 waters. Okay, we do need to know this portion being the slow step. That means that step 2 is the rate limiting step. So that's going to mean that for the kinetics of this reaction, it's all going to be based on step 2 happening. That's what's going to determine the amount of time that it takes. It's also important to know here that we can only get the rate law from data for multi-step reactions. So you can't just predict the rate law based on the equation. Since there are multiple steps and there are products and reactants that aren't being shown because they're made and then used up, you have to talk about the rate law based on an actual experimental observation of that reaction. Okay, so as I mentioned, the rate determining step is going to be the slow step. Okay, so this was reaction 2 in the case of the examples that we just had. The things that we highlighted and crossed out, those are our intermediates. So the N2O2 and the N2O, because they get formed in one step and then used up in another step, and they're not present overall in our overall reaction, we call those intermediate products. So they do get made, but then basically as soon as they get made, they get used up to make something else. So next I'd like you to take a moment and try to apply what we just talked about with multi-step reaction mechanisms to an energy diagram or a reaction profile for that. So as you can see, there are some words in a word bank on the side, and these are going to correspond to the different boxes on the graph diagram. So I'd like you to take a few minutes and see if you think you can place those just based on what we've talked about. And then you can unpause the video and see if you're right. So go ahead and pause and try that for yourself first. So hopefully you got at least this far with labeling the different portions of the graph. So essentially what you're looking at is that this is a two-step reaction. So this over here, this first peak is representing reaction 1. This second peak is representing reaction 2. And so these are our intermediates that are formed in between the two steps. Okay, so the trickiest part is figuring out which one is going to be the rate limiting transition state. So what you're actually looking for there is the biggest activation energy. So out of the two reactions, the first one, the peak is the highest. And so that's actually going to be our rate limiting step. And this is going to be our non-limiting step. Okay, and again, that's because the amount of activation energy needed is higher for this one. So if you want to talk about it in terms of fast and slow, this first one would be considered the slow step, and this second one would be considered the fast step. This is another figure basically summarizing that same concept from the previous one. And finally, I'd like to tie that together to the reaction mechanism we were looking at for the three-step reaction. So again, given the fact that reaction 2 is our slow step, and we have two different intermediates, we're going to have a 3-peak curve for this particular reaction profile. So reaction 1 was fast, so we're going to start at an arbitrary peak for that. Reaction 2 is our slow step or our rate limiting step, so we're going to need that to be the highest peak. And reaction 3 is also going to have a lower peak to make the products. Okay, so this is showing these portions here as our intermediates. So in the case of this one, this would be our N2O2. This would be our N2O because that's the intermediate from step 2 to step 3. And then again here for each of these peaks, that's where all of our reactants are smashed together so that we're making our final products. So that's more what it would look like for a 3-step reaction. But again, I mainly am just trying to reiterate the fact that your slow step is going to have the highest amount of potential energy for that activation energy. And that's it for this episode on kinetics. Thank you very much for watching. I hope you learned something.